Alrighty. Oh yeah, do whatever you need to do. You'll notice that you got bins sitting in front of you, and I know this is kind of weird for you guys. If you want to put, when you're done, kind of put your journals back in the bin on your table, that might be the best way to go. I had a couple kids ask me if they could keep the journal bins on the table. That's fine as long as you don't start adding like other stuff to it, like papers and things like that. All right, let's go ahead and get today rolling. The Meech. We got all these different forms of energy, okay, in the Meech. We talked about mechanical. Mechanical has to do with like motion, position, roller coasters, pendulums, moving water, wind, stuff like that. Electricity gets a little funkier. And I love teaching this, especially to 8th graders right now for the first time, because it is very, very abstract. When you learned about electricity the last time, it was probably 5th grade. And you probably like hooked up some wires and said, look, the electricity flows through the wires. Electricity is so much cooler than that. So my goal for today's class is for you to really understand what electricity is. Like, what is an electrical charge? When you get shocked, like, what is that? Why does it feel funky? That kind of stuff, when that happens, is what we're going to be talking about. So quickly, let's get ourselves moving through this. Don't write all the stuff you see here. In fact, all I want you to do is write this statement right here where it says all matter is made up of atoms. By the way, I'm going to say that 7 times this year in 7 different classes. 7 different journal lectures start this way. All right, so you can look at electricity as something that flows through a wire, or you can look at it like this, but I'm going to warn you, this is really stinking weird, and it's difficult to understand, but it's pretty cool. All you've written down is all matter is made of atoms. You got that? Good to go. All right. All matter is made up of atoms. Absolutely every single thing you can think of in the universe is made up of atoms. Hot dogs, grandmas, water, air, stars, okay, rocks. Every single substance you can think of is made up of atoms. There is no substance that you can name that is not made of atoms. Okay, that was relatively easy. That's an easy concept. Now behind me, I got the periodic table of the elements. You guys will know tons of stuff on here later. But all you need to realize right now is that this is a list of all the different types of atoms that you can make stuff out of in the universe. And back here, I can build anything that exists in the universe using these materials. These are the ingredients by which the universe is put together. And I can build hot dogs, rocks, oxygen, water, your grandma. I can build all those things out of this. Now, the recipe might be complex. The way they're connected together may be really, really, really intricate or not. But those are the building blocks of everything. In fact, in the universe, we really only use just a few of those to build things. The rest of them are all kind of extra. Now, that part is not that difficult. Where it starts getting really weird, and it's really fun to teach 8th graders this because your brains are just getting big enough to understand this. If I tried to do this with 7th graders, it'd be like, what? But 8th graders, you guys are really starting to be able to think about things that are extra complex. So watch this. I'm really going to try this. We're going to throw this way out there and jump probably immediately to the high school, college level. Everything is made up of atoms. Everything you picture, like your desktop, is made up of these atoms. Now, these atoms are all different from each other. Like if I were to build, let's say we lived in a Lego universe, let's just say, and you were a little Lego person, and like you walked out of your Lego house, you put on your little Lego hat, and got into a Lego car, but then you also breathed Lego air, which means the Legos would be little tiny particles that go in and out, and you took a shower in like Lego water. This would be really weird. That is like your Lego box from which you could build everything. Those are the different types of pieces of matter that you could have. So as you build something like this desk out of atoms, and by the way, the atoms are stupidly small, like stupider than you're thinking, okay? Like if I took a pin and I looked at the little tiny tip of it, like the smallest part that you could see, you'd be like this, looking at the little tiny tip of the pin. There'd be more atoms making up the tip of that pin than there are people on the planet times a trillion. Got it? So there's a lot of atoms. In this table right here, there are so many atoms comprising this tabletop that if I started counting them, it would probably take me millions, if not billions of years to even count them. You understand? Like 1, 2, 3. In fact, if I wanted to say the number of atoms that were here, it's 1, 0, 0, 0, 0. You'd probably come back in a week and I'd still be saying zeros. Okay? That's how many atoms are making up this thing right here. But they're stupidly small. Really, really small. So small they cannot be seen. Light is actually too large to bounce off of them to be seen. Now here's where it gets really weird. I'm going to try this. We tried it with the last class, and the other class was like, oh, that is weird. I'll try it with you too. This is all made of these little tiny particles. But, this is so weird, it appears to you like a solid object, doesn't it? I mean, the top of your table looks like something that's solid. But believe it or not, most of this is actually empty space. It's actually the space between the atoms. In fact, these atoms are really tiny and relatively small or far apart. For example, if I took a little tiny piece of matter smaller than an atom and I dropped it on the table, it'd probably go right through all those particles. In fact, when you take a look at this desktop, 99% of it is empty space.
What?
Okay? Just think about it for a minute. Now that, I know that sounds weird, like you're like, what are you talking about? How's that possible? You're actually kind of used to this concept. Have you ever gone up really close to a television and looked at it? What does it look like when it's on if you get real close to it? What does it look like?
It's like a lot of colors.
Well, a lot of colors, yeah, I definitely see that. What do you see when you get real close to it?
It has like little dots everywhere.
Yeah, it has little dots everywhere. If you get close enough to a TV and you look at it, you'll notice it's little tiny dots. In fact, these dots are so big up here that you might be able to see those little dots from your seat. Possibly. You might be able to see that that's actually dots. When you go up to your screen, you back away from it, it looks like a picture, but when you go up to it, you can realize, oh my gosh, look at that TV. It's little dots. In fact, when you look at your TV screen, you're watching TV, make sure you're listening to this one, most of the television screen is actually black when you're watching it. Isn't that weird?
Yeah.
And then all the little tiny dots, as you back away, your brain makes a picture out of. All right? Where you can see this really easy is a picture in a newspaper. You ever look really closely at a picture in the newspaper? It's little tiny dots. It's seriously, go home. You don't even need a magnifying glass. Go home, grab a newspaper, look at it like this, and you'll be like, oh my gosh, look, they're little tiny. Take a magnifying glass, you realize that most of the page in the picture is actually blank. And it's all these little tiny dots. Well, same thing here. Whole bunch of particles, but most of this is actually empty space. Now, that's just something I'm throwing at you. Most kids are not good with it until I show you what I'm going to show you in about 3 minutes in this little journal. Yeah, what's up?
If you said that light is too big to bounce off. Right?
Yeah, the waves of light are too large to reflect off those particles, yes.
You said that there's 99% space, so why can't light just shine through it?
Yeah, let's talk about that. That's a great question. Wait a minute. Light's too big to even bounce off it, so when you hold a flashlight under it, why doesn't all the light come through if it's all this empty space? I will show you, but I'm going to warn you, it's really stinking weird. All right, let me answer his question and show him. Now, behind me, here's an atom, right here. That's an atom. That's what an atom might look like. Okay, now, so how do you know what it looks like if you can't see it? Great question. Okay, we have lots of different tests that we can use to test those particles, but nobody knows what an atom looks like. This is a very common representation. You should be able to walk through the hall without disturbing someone's class fairly easily, okay, especially at this point in the year. All right, so let's check it out. You got, I know, they're a little squeaky, just trying not to break everyone's attention here. All right, so let's check it out. You have this thing hanging out right here. You got P, an N, and an E, all right? Now, you have 3 different parts to an atom. One starts with P, one starts with N, one starts with E. Most kids actually figured some out and raised their hand and told them to me. Do you know any parts of an atom? Just curious, give me one. What?
Neutron?
Neutron. Go ahead and write it down. We're going to write a little bulleted list. Might want to skip a line in between each. Cool, neutron is one. What's another, Amanda?
Proton.
Proton. Excellent. Some kids are saying, oh my gosh, they're right on the sheet. Yes, you're probably the last person to notice that. You're actually saying that out loud. Ian, what's the E?
Electron.
Yeah, electrons. Now, I'm going to answer that really cool question. I suppose it should be singular at this point. I'm going to answer that really cool question that you had. Why doesn't light just go through it? But it's going to take me a while to explain the answer. So let's go ahead and see what we got. Of all this stuff over here, these are made of protons, neutrons, and electrons. And each one of those protons and neutrons and electrons each carries a little charge. And that's where we're going to talk about electricity, but I want to divert and talk about his question for just a moment. If you take a look over here, the protons and the neutrons, and you're going to want to draw this if you haven't done it. Now, if you're wondering, how do I draw that? Just draw a few circles, like just a few, not even a lot, and like color half of them in. Okay, just draw a few circles, color half of them in. You don't need to, I don't even care how many you have, just have a few or several or whatever. Color half of them in. Then put some dark dots around the outside, okay? Don't do it 7th grade style where you have to tell everybody you're making dots. I'm making dots! Okay, just like little tiny scribbles are, okay? Perfect, now you have this really ugly atom thing going on, okay? You got a few colored in dots, or circles, you have a few circles that are not colored in, and then you have some dots around the outside. Perfect. Protons and neutrons both exist, and believe it or not, I'm still answering Hargrave's question about why doesn't light shine through the table. Protons and neutrons both exist in this place. This place right here is called the nucleus of the atom. Now some kids are like, oh, nucleus, like last year when we were learning about cells. No. Cells are alive, atoms are not. In fact, some kids like to write that down, that atoms are not alive. Some kids get really confused. The nucleus, the control center of it. No, you're thinking of last year, you're thinking of cells. Cells themselves, that's actually hard to say. Cells themselves are actually made up of trillions and trillions of atoms. Atoms are super, super, super small. So protons and neutrons exist in the nucleus, but electrons are the little things whizzing around the outside. And yes, it's fun to say whizzing in middle school. So the electrons are taking a whiz around the outside. There you go, Summer, that one's for you. Awesome! So far, so good. I thought we were learning about electricity, and I thought that kid asked something about light shining through a table and what now? Okay. Well, let's back this up. It's actually pretty cool. So this is an atom. Got it? Protons and neutrons are hanging out in this place called the nucleus. Electrons are whizzing around the outside. This is a heavy-duty concept. I think you will like it. Let me put this atom into motion for you. Okay?
Wow.
Yeah, wow, that's an appropriate response for this. Yes, the protons and neutrons hang out, and they move a little bit. They're hanging out in the middle. But notice the electrons. The electrons are freaking out. In fact, the way this is drawn is still not accurate because those electrons are probably actually moving to close to the speed of light. Now, the answer to your question is about 30 seconds away. Do you see that most of this is empty space?
Yeah.
You see what I'm saying? Most of this is empty space right now as we speak. Most of it is white blank paper. Yeah, now here we go. Those electrons are moving so fast that they blur. Okay? Now, you ever seen like a fan when it's on and the fan looks like a solid disc? Do you know what I'm talking about? It's blurry, but it looks like a circle. How about a helicopter going overhead? You ever see a helicopter where you can see the helicopter, but the rotary on the top, the rotor, looks like a blurry circle? Do you know what I'm saying? You know it's not a circle. You know it's just like two little things coming off like this. Well, the electrons move so fast that it forms like a cloud almost of space that's mainly empty space. Bring that concept over to here. And do you see why light can't get through?
Yeah.
Do you see why it appears as a solid object? And do you see how this could be mainly the empty space? That's messed up. Because I put my hands and it's like, oh. I know. Because the electrons are like attracted to each other and line up, and all of your atoms too are together, so your field can't penetrate the field of this. That's messed up. That's what matter actually looks like. And the whole point was, we're talking about electricity, which happens right after your question. Go.
Are like atoms different colors?
No, they're not. Because color has to do with the way light bounces off of them. So they drew them as different colors here so you can tell the difference between the pieces. But atoms, you can say, have no color because they can't be seen because they're too small. Okay, let's just forget that. That's freaky weird. I like it. All right, so how does this relate to electricity? Easy. Watch. Protons, you already have the word proton written, but you don't have this written, have a positive charge. That you do need to add, and I don't care where you add it. It could be in front of it, or behind it, or next to it, or over it, whatever works for you. Neutrons have a negative, yeah, that's not correct at all. Sorry, good thing I'm a science teacher. Electrons, oh, now I can't spell. It's all falling apart now. Electrons have a negative charge. And neutrons, that's why they're named what they're named, have neither charge. They have no charge. In fact, they don't take a side. They don't take a side as being positive or negative, so they are considered neutral. That's where the word comes from. So we can write down no charge, that's fine. Now check this out. You walking around right now are made up of hundreds of trillions of gazillions of bazillions, I don't even know the number, of atoms. Tons of them. And they all got protons and neutrons. But as I look at you, I know this is strange. Oh, I thought that one would. I'm starting to be a little bit off now. As I look at you right now, your body all, that one might. This one might. As I look at you right now, your body has the same number of protons as you have neutrons. So you're all neutral right now. Your atoms are all neutral. But we can change this, which is what we're going to do in a little demonstration right now. We're going to change this charge. So what I'm going to need you to do quickly is make a little table for me. Don't worry, we're almost done. We're getting close. I need you to make a little table for me. Okay, so it's not that little. And go right down at the bottom of the page. We're not adding much to it, so it doesn't need to be hugely substantial. But we're going to talk a little bit about electrical fields. I like the way this one progressed better than the last one. This one makes more sense. This had better flow. I like this one. So we're going to take a look at some electrical fields, okay? We're going to take a look at neutral objects, which for everybody I just poked in the head, I found out that you were a neutral object, which is good. We're going to take a look at negative objects, and we're going to take a look at positive objects. And then I'm going to show you something. You're on the edge. All I'm doing is just waiting for you to be done with the table here.
Do we have to write the attraction? Or
Yeah, you're going to have to at the end, so if you want to throw them down at the bottom, you can. That's fine. If you don't have room, they can go off to the blank page off to the left or whatever. It's fine. Okay, you just got to make sure you have all the elements here. Let's find out. All right, here we go. This part's actually pretty fun and easy. Now, when you're taking a look at all the atoms in an object like you, and the ones I poked in the head, you guys were neutral. You guys weren't carrying a charge, which means if I looked at all the atoms in your body, the millions and gazillions of them, you would have the same number of protons as you would electrons. It's supposed to be an S. So your protons and electrons are equal to one another. You have so many billion gazillion protons in your atoms and so many zillion gabillion electrons in your atoms. So you weren't carrying any charge. Now some of you have carried a charge before. You might have had one of those days where you just randomly get shocked off stuff. And not because you're sticking your finger in an electric socket, that's something else. But some of you have touched the doorknob before. Some of you have a couch in the basement. Every time you get off of it to go turn off the lights, you get a shock. Some of you guys get shocked when you get out of your car. Some of you guys get shocked when you go down the little spinny, roundy slide at the playground. Okay, we got all these different places where you can get shocked. One of the real common ones is if you're shopping for clothes. If you go to Marshall's or something like that and you flip, then you touch the metal. That's a great example. You can pick up these charges, but the way you do it is actually pretty cool. So hold on for 1 second. You can pick up a negative charge, which I'm going to do now. Okay. You remember the atom? Actually, I'll pop the atom back up there real quick. If we take a look at a picture of our atom, the protons, that's kind of annoying. The protons and neutrons are stuck in the middle. They're all stuck together. They can't go anywhere. But the electrons are capable of moving around. So you can actually make things negative, or you can steal electrons away from it and make it positive, which I know sounds really weird. Because those electrons are in motion, you can basically have electricity, which is kind of how it works. So let's take a quick peek. We said that, and I'm just going to, there we go. Must be you sitting there that makes this happen. Let's see, it's my famous group D. And then I learned that.
We're C now.
C.
Oh, okay. Yay! Okay, it's back. Perfect. Now I just need to put it back down. And I advance. And I pick it back up. Okay. So here I have protons, and I'm just catching up with you. Here we have protons equal to electrons. However, you can have situations where you have the electrons greater than, that's my alligator. You know what I'm saying? Some of you know what I'm saying when I say that. That's my alligator. Electrons greater than the number of protons. In that situation, you have a negative electrical field. Okay? Now, I'm going to go ahead and I'm going to put, in fact, there probably is still, just take a quick peek. Oh, there is. I mean, there is still an electrical negative, a negative electrical field going on over here. And I can sense it just a little bit when I walk over, so we're going to talk about it in just a moment. First, let's wrap this up. If you have more electrons than protons, you are negative. You are a negatively charged object. And right now, that thing is negative. You are all neutral, but that right now has a negative electrical field. Likewise, how about you just tell me? So what's something with a positive electrical field have? I'm actually slightly positive right now. I have a little bit of a charge because of what I've been doing today. And I'll show you what I'm talking about in just a moment. What's a positive electrical charge then? More protons than electrons. Cool, go ahead and write that down. Perfect. So let's watch. Okay, this is where it gets awkward and weird. Okay, let's not talk about it at all. Read, you okay? Just look away, read. Just look away. All right, great. As I sit and do this, the fabric of my shirt is actually giving electrons, because electrons are whizzing around the outside of the atom. The nucleus, the protons and neutrons are like stuck. The electrons are capable of moving. So what I'm doing is I'm putting tons and tons and tons of electrons onto that balloon. Since it now has more electrons than it started with, it has more electrons than protons, it carries a negative electrical field. And you can sense that electrical field, bless you, as you get close to it. Now, since I gave it, this could be a little confusing for you, so I need to see how many hands go in the air. Since I gave it my electrons, and made it so it has more electrons than protons, then what charge do I have? If I got rid of electrons, and my protons can't move, then what kind of charge would I have? Yeah. I'm positive. So now we can have some interaction of this electrical field. Watch very carefully. Watch very, very, very carefully. Very, very carefully. You don't want this. You see it already? As I get to electrical fields are invisible. They're completely invisible. You can't see them at all. But you can do weird stuff with it.
Magicians do that, right?
Yeah, they use static electricity a lot. Okay. Now here's something you gotta be really quick. That's super electrically charged right now for a balloon. It's actually really negative, which means there's a lot of electrons that want to get off of it. It has tons and tons and tons of electrons. So what I'm going to do is I'm actually going to steal some of them back, and you can hear them as they jump through the air. Listen really carefully, though. You gotta listen really carefully. Did you hear it? Oh, that was one too. Did you hear it? Did you hear the little clap? That's a spark noise. You've heard that noise before. That's actually electrons jumping off of that item and going back into my body. And as it does, it heats the air to thousands of degrees. And it expands. You hear that. It's like light. It is lightning. That's what it is. You just heard lightning. But it's very, very obviously weak lightning. All right, so let's continue to play here. Let's see how we're doing here. I can seriously do this all day. All right, so I got a question for you. Why does that balloon find me attractive? That's an awkward question. Why not? Why doesn't that balloon find me attractive? Why doesn't it? Why does it? I'm used to saying the other. Why does the balloon find me attractive? Yes?
Because it wants to be neutral.
Ooh, that's an interesting way to say that.
And you either have more positive or protons or have more electrons than it wants to.
What a cool thing to say. Nobody said that before. Yeah, the electrons want to get off of it and back to me. That's cool. I like that. I was looking for something different, but that's a really good answer. A really good answer. What do you think?
Because you're positively charged and the balloon is negative. negatively.
This answer's gonna take you a while, so I'm gonna play.
It's kind of like a magnet, and that positives and negatives attract.
There it is. I love it. Opposites attract. So since I have a positive and I have a negative, they want to get with each other. This is not appropriate at all. If you have low self-esteem, as many 8th graders should, it's perfect. You just draw a little face on that, and then be like, there you go. I got a friend. Follow you everywhere. You can break up with them to make yourself feel better. It's not me. It's not you. It's me.
No, it's not me.
It's not me. It's you. Perfect. So let's go the other route and see if we can do the other thing. Check this out. Let's go ahead and give it a couple more electrons. Look away. It's just awkward and weird. Okay,
I'm not old
perfect.
enough to see this.
All right. So let's see what we got here now. This one doesn't work all the time. I'm just going to let you know. I'm giving electrons to that, okay, to make that negative. And I've given electrons to this. Now I'm two-timing. This is bad. Okay. So now I'm giving electrons to this too. So now this has got a negative electrical field. So what's going to happen? Yeah.
We're just gonna push them.
Yeah, hopefully it's going to push. All right, so let's see very carefully. What? This is hard. Does not happen all the time because now part of this is negative and part of that is negative, which means they might twist away from each other too, so you got to watch carefully. You can definitely tell that's behaving weirdly as I bring the electrical fields close to each other. So let's take a quick peek and see if we can get anything going on. So now since, you can already see it, since they're both negative, you got some cool stuff going on. Okay, I have two negative. It's like an odd sport. Since they're both negative, there's a lot we got going on. They have the same charge, so they're going to attract each other. Sorry, they're going to repel each other, but then it's a stupid game. Awesome. So he just said that we're going to have these two things repelling each other because they have the same charge. So here I have a negative and a negative. They're going to want to get away from each other. So that right there is repulsion. That's what they're repelling each other, we can say. Just curious, what other two things would repel each other then? Negative and negative would repel each other. What else? There's another situation where you can get repulsion. Okay, what? What could happen? Positive and positive. Cool. And this happens sometimes. You get positive and positive. For example, like if I had somebody else and they were there, and then all of a sudden our shirts could repel each other, that one would be weird. What you see very often with this is like hair. Hair has a tendency to give away a lot of its electrons. So if you sit and brush your hair, or as Shane Kitty was saying, when he pets his cat, is that what he said? Good to know what Shane's doing at home. As he's petting his cat or brushing your own hair, you ever seen your hair start to stand up when that's the case? Yeah, your hair will actually repel itself. So you're doing one of these, which is, again, kind of a weird thing. I know. Ladies and gentlemen, here's what you got in front of you. Your flippant vocab has these 4 terms on it: proton, neutron, electron, and electrical attraction. So right now, take the next minute or so to find a couple of these. Don't rush. Make it go nice and slow. It's an easy one. Put a nice definition, then your pictures could be like of atoms with arrows pointing to the nucleus or around the outside. Your attraction down there at the bottom could be 2 positives, or I'm sorry, positive and a negative or something like that. That's your homework tonight, but it is not due.